Welcome back to the deep dive. Today we are tackling something that, well, it sounds incredibly technical on the surface. We're looking at databases.
Yeah, I know.
You hear database architecture, and you probably want to reach for the skip button or go grab a coffee. But stick with me here,
Right. Definitely stay with us.
because when you really peel back the layers, this isn't it's not actually just about computers. It's a story about chaos versus order. We're really looking at the invisible architecture that holds our entire digital world together.
It really is invisible architecture.
Hmm.
And honestly, it's kind of the only thing standing between civilization and total digital anarchy.
Total anarchy. Yeah.
I mean, if you think about the sheer amount of data flowing through our lives right now,
Mhm.
your bank transactions, online shopping, social media feeds, medical records, without a really rigid structure, it would all just collapse.
Just a mess.
Exactly. The source material we have today refers to that collapse as unstructured streams or fragmented entities.
Unstructured streams,
Right.
right? The digital noise. And the source we're looking at today, specifically this document called Relational Database Architecture, frames this whole thing as a blueprint for uh, structured intelligence.
Yeah, structured intelligence.
It's basically the rule book for how modern information systems think. But before we get into the solution, I kind of want to challenge the problem a little bit. The source talks a lot about flat file chaos.
Which is absolutely the enemy.
Is it though? Because, I mean, when I see flat file, I basically just picture a spreadsheet. And I have to be honest, I run my whole life on spreadsheets.
People do.
Right. I have a spreadsheet for my budget. I have one for my workout routine. It feels pretty organized to me.
Right.
Why is the source calling my beloved spreadsheets chaos?
Well, because you're operating at a human scale, not a system scale. A spreadsheet is perfectly fine for a grocery list or, a personal budget.
Right.
But imagine a major bank running on a single massive spreadsheet. Let's say you move houses. You call the bank to change your address.
Right. Simple enough. They just type in the new address.
Right, but in a flat file or spreadsheet world, your address might actually appear in 50 different rows.
Oh, wow.
Yeah, it's listed next to your checking account,
Yeah.
and then your savings account, your credit card, maybe that auto loan you took out 3 years ago.
I see where this is going.
So if the bank clerk updates row 40 but misses row 102, what happens?
I guess my bank statement goes to the new house, but my new credit card gets mailed to the old house.
Exactly. And now you have a massive security breach. You have conflicting truths in the system. That is what we mean by flat file chaos.
Ah.
It's a messy document. It has repetitive data, inconsistent formatting. It just doesn't scale. If you run a business on that, you have zero relational integrity.
Okay, that actually sounds terrifying.
It is.
So the goal here, our mission for this deep dive, is to figure out how to move from that terrifying mess to what the source calls RDBMS order.
Right. RDBMS stands for Relational Database Management System.
It's a mouthful.
It is a mouthful, yeah, but the concept is actually quite elegant. It's basically moving from one giant messy spreadsheet to a system of well-organized, much smaller spreadsheets that all talk to each other.
That talking to each other part is the key. So let's get into the mental model here. To explain this technical concept, the source uses an analogy that I think you can grasp, even if you've never written a single line of code.
It's a great analogy.
The school filing cabinet.
It's the perfect grounding image. Just close your eyes for a second and imagine a physical, heavy, blue steel filing cabinet sitting in a dusty school administration office.
Okay, I've got it.
In the world of databases, that entire physical cabinet is your database. But the real magic happens when you pull open a drawer.
Okay, I'm visualizing the cabinet. Smells like old paper and coffee. Let's unpack the drawer. In this analogy, a specific drawer, let's say the one labeled students, represents a table.
Right, a table. And the source defines a table as an entity.
Wait, let's pause right there. Entity. That sounds a bit like ghost hunting jargon. Can we strip that back? When a database architect says entity, what are they actually pointing at in the real world?
They just mean a thing.
A thing.
A distinct concept in the real world. So a student is a thing, a course is a thing, an instructor is a thing.
Got it.
So the student drawer is the table. Now inside that drawer, you have all those manila file folders. Each single file folder represents a row in the database.
So one physical folder equals one specific student.
Correct. That is a record. If you pull out the folder for John Smith, that entire folder is one row in your student table.
And on the tab of that file folder, the little plastic bit sticking up, you have a label. The source calls this the primary key.
That label is incredibly crucial. It's unique ID. Think about a physical cabinet. If you have two folders just labeled John Smith, you're going to get confused.
Right.
You might put John A's math grades into John B's folder by mistake.
Which would be a disaster for John A if John B is failing math.
Exactly. The primary key prevents that entirely. It's a strict rule that says every single folder must have a unique identifier. It's not just a polite suggestion, it's a foundational law of the architecture.
Okay, so we have the cabinet, we have the drawer, and the folders. But then there's this other thing, the foreign key. In the analogy, the source describes this as a sticky note taped to a folder that references a completely different drawer.
Precisely. It's a reference point. Think about it this way. If you want to know what math class John is in, you could technically stuff the entire 50-page math syllabus into John's little folder. But that would make John's folder massively thick.
Right. And if the syllabus changes halfway through the year, you have to go find John's folder and physically swap it out.
And not just John's folder. I'd have to swap it out for every single student taking that specific class. That sounds wildly inefficient.
Because it is. So instead of doing that, you just put a little sticky note in John's folder that says, See Math Drawer, Folder 101. That sticky note is the foreign key. It points directly to a primary key in another table. This physical analog really does help. It shows how it prevents the digital nightmares of losing folders or mixing records or duplicating IDs. It's really just about keeping things clean.
It's about way more than cleanliness, actually. It's about atomic precision.
Atomic precision. Yes, the atomic unit. The source mentions a one-concept rule here. This feels like the golden rule of organization that my incredible messy desk is currently violating.
It really is the golden rule. A table is designed to capture a single entity concept. You have a table for students, you have a table for courses, you have a table for orders.
Right.
If you try to store multiple concepts in one grid-like, say, putting the student's home address and the course instructor's salary in the exact same row, you are breaking the rules.
Why, though? I mean, I get that it's messy and kind of weird, but why is it actively breaking the rules?
Because it creates dependencies that shouldn't exist. Let's say the instructor gets a raise. Why should you have to edit a row that essentially belongs to a student?
Oh, I see.
You shouldn't. You should just edit the instructor table. Keeping them completely separate, keeping them atomic, means you can change one thing without inadvertently breaking another.
That makes a lot of sense. So looking at the anatomy of this grid, we have columns and rows. The source makes a really specific distinction here between attributes and instances.
Yeah, so think of the columns as the architectural rules. They define the attributes. For example, in a student's table, your columns might be student ID, first name, last name, and major.
Okay.
The column basically sets the constraint. It says, in this column, you can only put text, or in this column, you can only put a date.
So the column is basically the blank form you have to fill out, and the row is what you actually write into it.
Yes, exactly. The row is the instance. It's the actual real-world object populating that structure. So looking at the source data, we have a row that contains 1001, that's the ID, John Smith, and IT as the major.
So that row literally is John Smith, digitally speaking.
Digitally speaking, yes. That row is the instance of John.
Okay, let's zoom in on that ID for a second. The 1001. We touched on this with the filing cabinet label, but let's do a real deep dive into identity, the primary key. The source actually calls this the fingerprint of the data.
It's totally non-negotiable. A primary key has three main rules. First, it must be unique. Absolutely no duplicates allowed. Second, it cannot be NULL.
Null, doesn't that just mean zero?
In databases, NULL is actually much worse than zero.
How so?
Zero is a specific number. It's a value. NULL means void. It means absolute emptiness. You cannot have a blank cell where the ID should be. You can't have a student existing in the system with no identity.
Okay, that makes sense. And the third rule?
Permanent identity.
Yeah.
You generally don't change a primary key once it's signed to a record. Think about real-world equivalents like your social security number.
Ideally, yes, but hopefully managed a bit better than the government manages mine.
Fair point. But the core principle holds. Or think of a car's VIN, or a product's SKU in a store. Even if you change your personal name or you paint the car a completely different color, that core ID number stays exactly the same.
That stability is what allows the system to actually trust the data over time. Now, we mentioned the sticky note earlier, the foreign key. This is how tables talk to each other. The source calls it the bridge.
This really is the secret sauce of a relational database. I mean, it's right there in the name relationships. A foreign key is a field in one table that specifically links to the primary key of another table.
Let's use the example from the source slides to make this concrete for everyone. We have an enrollments table.
Right. In the enrollees table, you have a specific column for course side. Let's say the value sitting in that column is 200.
Okay.
That 200 is a foreign key. It points directly over to the courses table, where 200 is the primary key for a class called database design.
So in the enrollment table, we don't have to type out the words database design every single time a student signs up for it. We literally just type 200.
Exactly. The system sees 200 and instantly knows, oh, that's database design. It creates this context bridge without ever duplicating the actual text data.
Wow.
And if you rename the course later to advanced databases, you only change the text in one place, the courses table. Every single enrollment record linking to 200 is just automatically updated.
That is incredibly efficient. Now, this brings us to what I think is the tricky part. How do these things actually relate in the wild? The expert source outlines 3 specific patterns of relationship, and I feel like this is where people start to get confused.
It is, but we can simplify it.
Yeah.
These patterns just describe how rows in one table match up with rows in another table. The first one is the simplest. It's one-to-one.
Like a person and their passport.
Exactly. One row in the person table relates to exactly one row in the passport table. You generally don't have 5 valid passports, and a single passport doesn't belong to 5 different people.
Right.
But honestly, in real-world database design, this pattern is somewhat rare. You often just put that passport info directly into the person table.
Okay, so what's the most common pattern then?
That would be one-to-many. Think about a customer and orders. One customer, let's say you can have multiple orders.
Right.
You bought a book yesterday, a toaster today, and maybe shoes tomorrow. One customer, many shopping bags.
That makes perfect sense. One drawer for customers, one drawer for orders, and all those orders just point back to my customer ID. But then there's the really complex one, the many-to-many relationship.
Yes. This is where beginners always get tripped up, and this is where the simple filing cabinet analogy needs a bit of a twist. Think about students and classes.
Okay, one student takes many classes.
Right. But also, one class contains many students. Many rows relate to many rows. It goes both ways.
So if I'm the database architect building this, how do I actually record that? Do I go to the student table, find John, and in his class column just write a big long list like biology, math, English?
You absolutely cannot do that. That is the forbidden move in database design.
Why? I mean, it seems like the easiest way.
Because now you have a list trapped inside a single cell. How does the computer search that?
Oh.
If I say, find me everyone taking math, the computer has to crack open and read inside every single text string to see if the word math is hidden in there somewhere. It's slow, it's messy, and it completely breaks the structural integrity we just built.
Okay, so I can't write it on John's folder. And I obviously can't go to the class table and write a list of 500 students in the biology row.
No.
So how do we actually solve this?
We need a middleman. We need what's called the junction table.
The source calls this the enrollments table, right?
Yes. Visualize this. You have the student drawer on your left. You have the course drawer on your right.
Okay.
You want to put John into the biology class. You don't touch John's folder.
Yeah.
And you don't touch the biology folder.
Okay, so what do I touch?
You grab a third, completely blank sheet of paper and put it in the middle.
The junction table.
Exactly. On that middle sheet, you write 2 numbers and 2 numbers only. John's ID, which is 1001, and biology's ID, which is 200. That's it. It's just a list of pairs.
So the junction table is literally just a massive list of IDs matching up with other IDs.
That's all it is. One row says student 1001 is in course 200. The very next row says student 1001 is in course 300. It beautifully resolves the complex many-to-many logic by breaking it down into 2 simple one-to-many relationships.
It's almost like a diplomat standing between them, making sure the 2 big tables don't get into a fight.
That's a great way to put it. It keeps the main tables completely clean and creates a dedicated space for the relationship itself to exist independently.
Speaking of keeping things clean, let's talk about hygiene. The source brings up a concept called data normalization. It contrasts unnormalized data with normalized data. Now, hygiene sounds a little boring. It sounds like flossing.
It does sound like flossing, but let's reframe it. Don't think of it as hygiene. Think of it as risk management. Or better yet, preventing Schrodinger's data.
Okay, now I'm interested. How can data be Schrodinger's cat?
Well, the source explicitly warns about anomalies. In a database, an anomaly is basically when the truth splits in half. You have 2 records saying completely different things about the exact same person.
Give me a specific example of that.
Look at the unnormalized table in the source document. It actually lists student John twice. Once for his computer science class, and again for his English lit class. And in both of those rows, it lists his name, John.
That seems fine. I mean, his
Yeah.
name is John.
It's fine right up until John decides to change his name to Jonathan. That is called update risk.
Ah.
If a database clerk updates his name in the first row, but completely forgets about the second row, the database now thinks there are two different people, John and Jonathan. Or it just has conflicting information for one ID. Which one is true?
The truth has split. The database is fundamentally broken at that point.
Exactly. So the fix, which is normalization, is separating that data out. You put John in the students table once, just once. You put the classes in the course table once, and you use that junction table we just talked about to link them together. That removes all redundancy. If John changes his name, you change it in one single cell, and the entire system updates instantly.
Let's apply this to something you and I use all the time, e-commerce. The source has a great diagram here of an online store. It shows a chain. Customer connects to order details, which then connects to products.
This is a classic real-world application. Imagine you are selling a pair of headphones. You have a products table with a row for noise-canceling headphones. It has the price, the technical specs, the really long marketing descriptions.
And I assume millions of people are buying these headphones.
Hopefully. Now, without this relational architecture, if 1 million people bought them, you might be tempted to just copy and paste that long product description into every single order record.
That would be gigabytes of wasted space just repeating the same paragraph about crisp highs and deep bass.
Exactly. But with this normalized structure, the order details table just points to the product ID. You reference the single headphones row 1 million times, but you never actually duplicate the description text. It's incredibly efficient. It's what allows global scale.
Okay, so we've got the structure figured out. We have the filing cabinet, the relationships. But how do we actually tell the database what to do? We need some kind of language.
We do. And that language is SQL. Structured query language. It's the universal tongue for speaking to these relational databases.
I've seen SQL code before, and honestly, compared to other programming languages, it looks weirdly human. The source breaks this down into 4 key verbs. They call them the CRU dubs.
CRUD is the acronym developers use all the time. It stands for create, read, update, and delete. In SQL, those concepts map to specific commands.
Right.
To read data, we use select. To add data, we use insert. To modify data, we use update. And to remove data, we use delete.
And the syntax is surprisingly readable. The example in the source here is select first name from students where major equals IT.
It reads almost exactly like English. But I want to connect this back to our filing cabinet analogy. Think of the old way, the manual way. As you literally walking into that office, pulling open drawers, flipping through hundreds of folders, and looking at every single one to see if the student happens to be in IT. It takes forever.
That would take days.
SQL is like sitting in a comfortable chair and shouting at a super intelligent assistant, hey, bring me the first names of everyone in IT. You don't care how the assistant finds them.
You don't care which drawer they are in.
Exactly. You don't care about the drawer. You just declare what you want.
It's declarative. That's the specific term the source uses.
Exactly. You tell the database what you want, not how to go get it. The engine figures out the how.
Now, here's where it gets really interesting for the enterprise and business side of things. Why do major banks, healthcare providers, and governments trust this specific type of database over anything else? Why not use something newer or fancier? The expert source points to one single acronym, ACID.
ACID is the gold standard. It stands for atomicity, consistency, isolation, and durability. And honestly, it's a primary reason you still have money in your bank account right now.
Let's really break that down because atomicity sounds like a bomb.
It effectively is a logic bomb. Atomicity means all or nothing. Imagine it's Black Friday. You are online buying the very last big screen TV in stock. You click buy.
Okay, my heart is racing.
The server subtracts the TV from the inventory. But, and here's the drama, milliseconds before it charges your credit card, lightning strikes the data center. The power cuts completely.
Oh no. So what happens? Do I get the TV? Do I get charged for it?
Without ACID, you might end up in a really bad state where the shop thinks the TV is sold so no one else can buy it, but you never actually paid for it. The inventory is gone, the money is gone.
Right.
It's a limbo state.
That's a nightmare for the store.
But with atomicity, the database treats the inventory deduction and the payment as a single unbreakable atom. If the power fails halfway through, the database simply rewinds time.
It rewinds time.
It cancels the inventory change entirely. When the power comes back, it's like your click never happened. The TV is back on the shelf.
That is huge. It saves us from half-finished errors.
Then you have consistency. This just means the database rules are absolute law. You can't break the rules we set up earlier, like the unique ID rule. If a program tries to enter a student without an ID, the database just says no. It rejects the entry flat out.
What about isolation?
Isolation means my transaction doesn't interfere with your transaction, even if they happen at the exact same millisecond. If we both click buy on that last TV at the very same time, the database lines us up invisibly. One of us wins, one of us loses. It never accidentally sells the same TV to both of us.
And finally, durability.
Durability is the ultimate promise of permanence. Once the database successfully sends a message transaction saved, it is saved forever. Even if the server physically catches fire the very next second, that data has already been permanently written to the hard disk. It survives the crash.
Data integrity is non-negotiable. That's a direct quote from the source. It really does sound heroic when you put it that way.
It is heroic. In a world of completely fleeting digital interactions, RDBMS offers a rigid guarantee that what happened actually happened. It creates a bedrock of absolute truth.
As we wrap up this deep dive, it's really worth noting the broader technology landscape. The source mentions that while there are different engines out there, some are open source like MySQL or Postgres, and others are proprietary like Microsoft SQL Server or Oracle, the underlying logic is universal.
That's the real beauty of it. Whether you are a tiny startup using free open source tools or a massive global corporation paying millions for Oracle, you are using the exact same physics.
Yeah.
You're using tables, keys, and SQL. The core blueprint doesn't change.
So to recap that blueprint from the source, we've really got 5 pillars here. Storage, which is organized into tables or entities. Identity, those primary keys that uniquely identify every single row. Connection, the foreign keys that link tables via those virtual sticky nodes. Language, which is SQL, the smart assistant we shout commands at. And finally, hygiene, which is normalization to prevent the truth from splitting into anomalies.
That really is the foundation of structured intelligence.
It changes how you look at the world, honestly. The next time you order food delivery on your phone or check your grades online or buy a concert ticket, I really want you to visualize those invisible junction tables and foreign keys firing off in the background.
It's a massive, entirely silent machine, keeping the digital world from returning to that flat file chaos we started with.
And without that rigid, invisible structure, none of this modern digital magic would be possible. That's all for this deep dive. Thanks for listening.